Here is Bruce Berndt, who doesn't need any introduction, I don't think. He's going to talk about integrals associated with Ramanujan and elliptical functions.
Thank you, Dan. So it's been a wonderful conference, and it's really an honor to be invited to speak amongst all the many lectures that have been given at the conference. But begin with the usual cue notation. So this talk is actually motivated by extremely unsuccessful attempt to find simple proofs of transformation formulas for these two 10th order Mach data functions. So I've been working on this for over a year, much as George Andrews has been working on a conjecture for over a year, and I've had no success whatsoever, but this is motivated to what I'm going to talk with you about today. So these are the two transformation formulas which were proved by Yun-Sa Che about 13 years ago in a wonderful paper. The proofs, however, are very long and complicated, and I've been attempting to find, without success, simpler proofs. Let me try to convince you how beautiful these formulas are. So I'm using Ramanujan's notation. N is not an integer. We would normally replace n by I tau, where tau is in the upper half plane. So we would have here, this is one of the transformation formulas at I tau, or tau. And here we have then minus 1 over tau, but now we don't have just one of the Mach data functions appearing, but we have both of them appearing with tau replaced by minus 1 over tau. And also this 1 over square root, this is very common if you have weight minus 1/2, modular form or theta function. But then we have these beautiful integrals also appearing in the transformation formulas. So they're very similar. Again, here the phi is replaced by psi, and both phi and psi appear in the transformation formula. So what I did is to look for integrals which are similar shape and see if by examining these similar integrals I might have some ideas about these integrals, but unfortunately that not turned out to be the case. So here is the reference to Yun-Sa Che's wonderful paper. Okay, so let me define the complete elliptic integral of the first kind, which is associated with the modulus k in the theory of elliptic functions. And we let k prime be k of small k prime, where this is the complementary modulus. So in a lecture last summer that Dennis Stanton gave in Orlando at a meeting for Murad Ishmael's 70th birthday, he mentioned this result, which arose in the paper of Murad Ishmael and Berndt some years ago. I'll indicate how this arose. But note that the value of the integral is independent of k and k prime. So the integrand is the weight function of a sequence of polynomials arising in the Hamburger moment problem. And in correspondence with Dennis Stanton, he said that in research he had conducted with Jung-Soo Kim, the nth moment is the generating function for certain k-colored up-down permutations. But I'm not going to discuss that. And then besides Dennis Stanton's lecture in Orlando, there's another lecture given by Murad Ishmael himself at NIST last summer, in which he also asked for a direct proof of this formula. So Stanton informed me that Kuznetsov has found an independent proof, and I have also found the proof, but I would would like to mention that the first part of the proof was actually supplied by Chawla in 1928. Just as a personal aside, I might mention that the first mathematician with whom I ever co-authored a paper was Chawla, but I would like to emphasize that my collaboration in 2 published papers with Chawla occurred after 1928. So here is the reference to Ishmael and Balat's original paper, and this is also discussed in Murad's book. So that's one motivation, and I'll come back to that. So here is another motivation. This is an integral that Ramanujan submitted to the Journal of the Indian Mathematical Society. So it's sort of an aberration of a familiar integral, that is the integral of sine nx over x, which has the value pi over 2. So if you divide by 2 things, well, it's natural, then it should be pi over 4. So the first proof was actually supplied by A.C.L. Wilkinson. 4 years later, Wilkinson was actually an English man who was teaching in Madras for much of his career. So there's a beautiful proof of this result due to Thurl Venkatachar and Venkatachala Iyengar, who in their retirement years, over a period of several years, combined to develop proofs of some of Ramanujan's most intriguing formulas. So let me just say a few words about these 2 people, since I think many of you are not familiar with them. So Thurl Venkatachar was a physicist, and Venkatachala Iyengar a mathematician. They knew each other for most of their lives, and they happened to retire in the same area of Bangalore. And they would take evening walks together. Usually, Venkatachala Iyengar was in front of Thurl Venkatachar. And they would discuss mathematical problems, especially of Ramanujan, on these walks. And then they accumulated all of their findings in some handwritten notes. And Venkatachala Iyengar gave me a copy of these notes many years ago, and I actually used a few of their proofs in my books, on the notebooks in my books with George Andrews on the Lost Notebook. So with 4 of my former students, we have now prepared an edition of these notes, and these will be published in a volume published by the Ramanujan Mathematical Society. So here is the reference. Elementary levels has to be interpreted a little bit broadly, but we hope that our presentation of their proofs will be clear. So it's actually in press and should be out pretty soon. So I'll indicate another proof of this in this lecture. And the ideas in both of the proofs of these results can be used to evaluate other integrals as well. And I'd like to express my indebtedness to Chawla. He had evaluated some of these integrals by somewhat different means. And in our evaluations, we'll actually use some results of Ramanujan connected with the theory of elliptic functions. And we also use Fourier series of elliptic functions. And we'll use Ramanujan's change of sign process. So many of you probably do not know what this change of sign process is, so I'll briefly describe it. So suppose we have some sort of relation in the theory of elliptic functions, and now I'm now going to convert to Ramanujan's notation. He lets x be a squared, q is e to the minus y, and y is this quotient of complete elliptic integrals. then one of the main theorems in the theory of elliptic functions and the main theorem in Ramanujan's work is that this familiar theta function squared is just equal to 2 over pi times this complete elliptic integral, and that can be expressed in this hypergeometric series. And if you'll recall the movie The Man Who Knew Infinity, which we saw a couple days ago, when Ramanujan rushed to the board to get his simple proof, it is exactly of this formula right here. This is what was in the picture. This is much more difficult. So suppose we have some relation involving x, q, and z, which is what Ramanujan used for this hypergeometric function, and you want to replace q by minus q. Well, your first thought is, well, that's very easy. Just replace q by minus q. But you have to remember that these variables are all intertwined in this way. So you have to do a little bit more. So what you have to do is to replace the x by x over 1 minus x, q replaced by minus q, and the z has to be replaced by z square root of 1 minus x. So this is the change of sign process. Okay, so let's go back to the original integral that for which Dennis Stanton and Murad Ishmael in their lectures asked for proof which is independent of their moment theory. So let's first evaluate this integral where k and k prime are both equal to 1. This would mean that x is equal to 1/2. So I'll replace x by minus x in the integram, and note that cosine of it is quotient t. So we get this then. And then I'll set x to be u squared, just simple change of variable. So the original integral then becomes 4 times this integral. So usually in complex analysis, the first course, when we evaluate integrals, we integrate over a semicircle to include minus infinity to infinity. Here, I'm not going to integrate over a semicircle. I'm going to integrate over a quarter circle. So I'll integrate over this quarter circle of radius cap r. So my path of integration is from 0 to r, the quarter circle, and then back on the imaginary axis. I will let r tend to infinity and assume that I let r tend to infinity on some sequence of values so that I remain at a bounded distance from the poles of the integram. So I'll skip all the calculations, but upon using the residue theorem, we get then this series evaluation for this infinite integral. So then it would be nice if one had, a simpler representation than this series. Okay, well, entry 16I in chapter 17 of Ramanujan's notebooks actually provides then a value of this infinite series. The series we have is when y is equal to pi, but Ramanujan here has a much more general evaluation. But I will only use that special case here when y is equal to pi. So then this means that k and k prime are the same, and x is equal to 1/2. And z of 1/2, this hypergeometric function at x equals 1/2, has a very familiar value. And so then when we go back to the series representation and use this evaluation, just plugging in, we get, I just use the reflection formula for the gamma function to put the value of the integral in a different form. So that's the valuation of that integral. So this was also established by Chawla. He actually made a miscalculation. He has an extra factor of 4 in the denominator. Okay, so this again is the statement of the theorem of Ishmael in Alladi. And so again, when k is equal to k prime, or k is the square root of a half, or x is equal to a half, then this reduces to what we previously evaluated. Okay, so now how do we proceed to prove this evaluation independent of the Hamburger moment theory? So I won't provide all the details by any means, but what I did is to make a change variable. I let k squared be cosine squared of a half theta, so then k prime is just sine squared of a half theta. So, and then I'll let f of theta to be equal to this integral, again, of Ishmael and Alladi. So the strategy is to show that f of theta is independent of theta. So we evaluated f of theta in one particular case, namely when theta is equal to a half pi. So if we can show that the derivative of f with respect to theta is 0, then we are finished. So I won't. I'll stop here. I won't actually carry through that work. So let me just say a few words about some more general formulas. Okay, so remember after the change of variable that I made at the beginning, we would get this integral when a is equal to 0. So we might then ask for this more general evaluation, which actually occurs again in the Ishmael-Alladi theory. So by generalization of the argument, which I just gave you a few moments ago, we can evaluate this integral. So we have this evaluation. So now we have this more general power here of 2n plus 1 of the sum n. So if I let a to be actually equal to an odd positive integer, then this series on the right-hand side is actually equal to 0. Yeah. Well, this follows in more than one way. It follows from this evaluation. Clearly, if I let a be 2r plus 1, then this is 0, and so therefore the series is equal to 0. So I don't get an evaluation of the integral in this case. I get evaluation of the series. So that identity actually can be established by several means. It was first established by Cauchy. It can also be found in Ramanujan's second notebook. And furthermore, he submitted that as a problem to the Journal of the Indian Mathematical Society. So there are several, let me make one more comment. You can also evaluate for special small values of r through the theory of elliptic functions and results in Ramanujan's second notebook. That's because Ramanujan has a more general formula, not just with pi, but with pi replaced by y. And there have been many proofs of this formula in the literature. Okay, let me let a be an even positive integer, 2r. So then we have an evaluation of the integral in terms of this infinite series. And so then the question is, can you evaluate the infinite series that arises here? So again, in particular cases, we can use results from the theory of elliptic functions. So again, in entry 16, triple I in chapter 17 of Ramanujan's second notebook. We have this more general formula for evaluating this infinite series in terms of z and x. So we just want the evaluation when y is equal to pi then. Okay, so this is the particular case when r is equal to 1. So you let x be a half and y equals pi, or then you get this evaluation. This actually was also proved by Chawla. So we can evaluate further integrals of this type with the x to the 4r plus 1 in the integrand by using identities from the theory of elliptic functions, which again are found in Ramanujan's work. So let me turn now to this other integral, which has been evaluated from this problem that Ramanujan posed, and which was evaluated, as I said, by Berndt and Venkatacharya-Iyengar. So again, I just repeat that there's a beautiful proof of this by Berndt and Venkatacharya-Iyengar, which you can find in the monograph that is under publication. So we can give another proof by contour integration. My proof is not as good as Venkatacharya-Iyengar and Venkatacharya's proof. And then we can also generalize this result. So if b is any positive integer congruent to -1 modulo 4, and n is any positive odd integer, then we have this evaluation that this integral is actually equal to 0. And the different proof is given by Chawla again. Okay, and here is another theorem, and note the difference. I now have a minus sign in the denominator instead of a plus sign. So again, by similar kind of argument, integrating over a quarter circular contour, we can evaluate this integral in terms of this infinite series. So again, the problem is to identify this infinite series more precisely. So here the method that I used were a little bit different than the previous methods. So here, I'll use the Fourier series for the Jacobian elliptic function Sn of u squared. So you'll just have to, this is in Whittaker and Watson's book, for example. The A0 here, which I actually really do not need, is written in terms of the complete elliptic integral of the first kind, and E, the complete elliptic integral of the second kind. So here I've just translated from this Fourier series into Ramanujan's notation. So now I'm going to apply the change of sign process. So again, this is what we have to do. X goes into x over x minus 1, q into minus q, and z into z times the square root of 1 minus x. So the reason I'm doing that is, if you'll notice in this series, I do not have a minus 1 to the n, whereas in the evaluation which I gave you a moment ago, there's a minus 1 to the n there. So this is the reason why I'm using the change of sign process to introduce a minus 1 to the n into the process. Okay, so let me just briefly do that. Okay, so after the change of sign process, we actually get this series. So note my minus 1 to the n there. And now I just expand this cosine in a power series, it's Taylor series about 0, and invert the order of summation, and this is what we get. So now note, we have exactly the kind of series that arose in the evaluation of our integral. But now they are part of coefficients of a power series in U. Okay, so what we have to do is to go back to the Sn squared function and calculate its power series. Well, let me just indicate that first, here are the first then coefficients of u squared, u to the fourth, u to the sixth of this power series. And what I actually found it more convenient to do is to use the power series for the Jacobian elliptic function Cn u squared. Okay, so I won't give you that. I'll have to apply the change of sign process, of course, to the power series for Cn u squared. Okay, so I won't give you all that power series, but it turns out that the coefficients of, for example, u squared, u to the fourth, and u to the sixth are just 1, 0, and minus 1/5 respectively. So then this then enables us to, when we compare the two sets of coefficients, we're able then to evaluate these series. So again, I've only given the first three, but one could evaluate any particular, for any particular case. Okay, the first evaluation is in agreement with Chawla. The third one is not in Chawla's work. So the second one is actually a special case of a more general result. Okay, so let me go back. This is the general formula that we have. I only gave you the values of the series, so I'm just using now the values of the series to go back to our original problem of evaluating the integral. So if nu is equal to 0, then using the series we got this evaluation, and this is also done by Chawla. And this is the next case. Okay, let me go back to this series that was equal to 0. So it turns out that if I have any power of n congruent to 1 modulo 4, that this series is equal to 0. And this is an easier result to prove. It actually goes back to Cauchy again. And there are many other proofs in the literature, and I've just given a few of them. Nanjandaya actually was a professor at the University of Mysore for many years, and on one of my visits to Mysore, we actually wrote a paper together. Okay, so I think that's about all I have to say, so thank you very much.
Any questions for this?
The book was about to appear by the two gentlemen with all the time was written for school children.
Yes. Okay. Yes. That's why I sort of hesitated when I showed you the title, which is Ramanujan at Elementary Levels Glimpses. Yes. Yes. So there are some things in the book which school children can understand.
Very few.
Yes.
Jeff?
The question, but I'd like to think this slide on the changing the sign, the original changing the sign that just like to stare at it if you slide way at the beginning of your talk. Now you through many integrals.
So that's the,
Yeah.
Keep going, keep going.
you want to,
The original thing has a completed elliptic integral and there is a data function in case of advanced. That slide, yeah.
Okay, other questions? Yes.
What about hyperelliptic integrals?
so what is a hyperelliptic?
So you place, so elliptic control is just we have square root of cube with a coordinate on the bottom, and then elliptic is replaced with higher
Yeah, I don't know anything about that. Sorry.
There were no instances.
There were no what? No, I didn't do it. Instances of hyperelliptic integrals? No, not that I know.
Yes.
What?
Can you put the formula for the moments again when you hold the series?
So the integrals that,
The integral with an x to the n as a series.
so
So I think it was.
that those?
Yeah. You see, I think what this is you're giving a different measure for the same moment problem. And this is very interesting because the measures that make the polynomials orthogonal in the corresponding L2 space are discrete. I don't know if this is one of them or not. So if this is indeed one of these extremal ones which make the polynomials discrete, make the polynomials complete in their L2 space, that would be very interesting. But if you look at the formula, it's really a moment of a discrete measure. So I think there's more to it.
Okay, well, good.
Okay.
Well, perhaps I gave you something to think about.
Okay.
Yeah, maybe one more question? Okay, well, let's